All right, so we're doing problems from chapter 11. Okay, this problem says a rigid body with a cylindrical cross-section is released from the top of a 30-degree incline. It rolls 10 meters. 10 meters is roughly from here to the wall. Okay, 30 degrees would be an incline, let's say from the ceiling to here, to where I'm sitting. Okay. And it rolls 10 meters to the bottom in 2.6 seconds. Find the moment of inertia of the body in terms of its mass and radius r. Okay. Now, if you'll recall, if you have an angle of incline theta, if you have an object that is sliding down frictionlessly, let's say an ice cube, the acceleration of this would be g sine theta. Okay. Now, on the other hand, if you have an object rolling down without slipping on the same incline, the acceleration of the center of mass is less than this guy. Okay, and the acceleration is given by, for this guy, the acceleration of the center of mass is given by g sine theta divided by 1 plus I center of mass divided by mr squared. M is the mass of the guy and r is the radius of the object. Okay. So see, this number is greater than 1, so the acceleration is less than that of an object sliding down frictionlessly. All right, so this object covers 10 meters in 2.6 seconds. Okay, so let's calculate the acceleration of this guy. Okay, so we'll use this formula: x minus x naught equal to v naught t plus 1/2 at squared. Okay. And our x-axis is this way. Okay. X minus x naught is 10 meters. V naught, the initial velocity was 0. Okay, so 10 meters is 1/2. All right, I'll do. T is 2. A is 2 x minus x naught divided by t squared. Okay, 2.96 meters per second squared. All right, so now we're going to plug that in here and calculate this ratio. That's what they're asking us to do. So A is g sine theta, 1 plus I center of mass divided by mr squared. Okay, so 1 plus I center of mass divided by mr squared equal to g sine theta divided by A, I center of mass, mr squared. Yeah. All right, so this is 9.8 meters per second square sine 30. Okay. These units cancel. This is a dimensionless number. Mhm. Okay, it works out to 0.66. So the center of mass is 0.66 mr squared. So the moment of inertia of the object that was rolling down the incline is 0.66 times mr squared, 2/3 mr squared. This problem says a solid cylinder rolls up an incline at an angle of 20 degrees. If it starts at the bottom with a speed of 10 meters per second, how far up the incline does it travel? Okay, so what we'll do is this is 20 degrees and it's rolling up the incline. The center of mass velocity is 10 meters per second. And we want to find out how far up the incline it travels. Okay. And this will be the height. All right, so what we'll use is, again, you can use the same formula for the acceleration. Okay, so rolling down the acceleration and deceleration, it'll be the same expression for acceleration. Because except that, let's solve it differently. We'll use energy conservation principles. Okay, so here you have rotational energy, kinetic energy, and translational kinetic energy. And when it gets up there, that becomes gravitational potential energy. Okay? So initial energy equal to final energy. Initially it has 1/2. They tell you it's a solid cylinder. I omega square plus 1/2 mv square equal to mgh. Okay. So that's how high the center of mass rises. Okay. Now omega and v are related. V equal to r omega. Okay. And for a solid cylinder, the moment of inertia about the center of mass is 1/2 mr squared. So you have 1/2 I is 1/2 mr squared, and omega square is v squared over r squared. Okay. So this I got replaced by that. This omega got replaced by v by r. Okay. So at the bottom of the hill, what this is saying is the r's cancel. 1/4 mv square plus 1/2 mv square equal to mgh. Okay. So you see, this is the rotational kinetic energy. That's 1/2 of this. So the translational kinetic energy is twice the rotational kinetic energy. Okay. For the cylinder. All right, so the m of course cancels. So all cylinders would go up the same height. So this is 3/4 V square equal to GH, H equal to 3 into 10 okay. And so this works out to 7.65 meters. Yeah. And so we'll calculate the distance to the incline. Okay. $22.4 meters. So it'll go up the incline 22.4 meters. Again, roughly the width of this room. Okay, so this says a Formula One racing car with a mass of 750 kgs is speeding through a course in Monaco and enters a circular turn at 220 kilometers per hour. Okay, so that's about half the weight of a small car. Okay. And this going in a counterclockwise direction about the origin of the circle. At another part of the course, this car enters a second circular turn at 180 kilometers per hour, also in the counterclockwise direction. If the radius of curvatures of the first turn is 130 meters and that of the second is 100 meters, compare the angular momenta of the race car in each turn taken about the origin of the circular turns. Okay, so let's calculate the velocities. The first turn is 220 kilometers per hour. We'll convert these to meters per second. That's 1,000, and an hour is 3,600 seconds. So it's just dividing this by 3.6, the conversion factor. And the second velocity is 50 meters per second. When an object is going in a circular path, the angular momentum is given by L is mvr. Okay. So around the first turn, it's mv1r1, and that's 750 kgs. CH11 is 61.1 meters per second, and R1 is 130 meters. Okay. So this is 5.96 into 10 to the power 6 kg meter square per second. Similarly, the angular momentum about the second turn is mv2r2 and this is equal to 3.75 into 10 to the power 6 kg meter square over second. Okay, those are the angular momentum. Okay. What we'll do is that the problem doesn't ask this, but we'll calculate the centripetal acceleration. Okay, this will give you a better sense for what's going on. Okay, so the centripetal acceleration about the first curve is v1 squared divided by r1, 61.1 meters per second squared divided by 130 meters. And I'll calculate this in terms of G's. Okay. So okay, so around the first turn, the centripetal acceleration is 2.93 Gs. Okay, that's about the maximum Gs that an astronaut feels going up to space. All right. So going around the turn, what is giving the car that acceleration? It's the static friction force. The tires are sticky. Okay, and so if you're turning like that, the seat is pushing you in that direction. Seat belt, and all that kind of stuff, with the force 3 times your body weight. Okay, so that's pretty strong G's. The acceleration, centripetal acceleration around the second curve is 50 meters per second squared divided by 100 meters. Okay, so the first curve is bigger, the second turn is sharper. Okay, and so this acceleration is 25 meters per second squared. .55 Gs. So the centripetal acceleration around the second curve was that. Okay, you see the tires are sticky enough to have a greater acceleration. So why do you think the car might have slowed down around the second curve?
Because we didn't flip.
Hmm?
So the car wouldn't flip on it.
Well,
The angle of the bank?
no. Mm, it's probably crowded. Okay? Anyway, the point is the car could make a faster turn. Okay. Well, these Formula car races are on flat road. Okay. This problem says at a particular instant, a 1 kg particle's position is that, its velocity is that, and the force on it is this. What is the angular momentum of the particle about the origin? So the angular momentum, you guys can check out the formula, is equal to R cross P. Equal to R cross M times velocity. Okay. So it's a matter of finding the cross product of the two, R cross V. So we'll do it like this. You guys remember what is I cross J? So I, J, K. I cross J is K, J cross K is I, K cross I is J, and so on. And I cross K is negative J. Okay, so this is equal to, so let's, I cross J is K, and so on. J cross K is I, and all right, so L is, M is 1 kgs, and R is 2I minus 4J plus 6K, and V is minus I plus 4J plus K. Okay, and the units are all, so I'll write it 1, and the unit is kg meter square per second. Kg from there, meters per second from here, and then another meter from here. Okay. All right, now it's a matter of just doing cross products. Okay, so we just will use these rules. I cross, oops, there's the, I forgot the cross. Okay. So I cross I, what is I cross I? I'm sorry? Yeah. So any vector crossed with itself is 0. I cross I is 0. I cross J is K. So that is 2 times 4 is 8K. And then I cross K is? I cross K is negative J. Okay. So I cross K is negative J, so minus 2J. Okay. And then J cross I is negative K. Yeah. J cross I is negative K. So 4 times 1 minus 4K. Minus or minus was plus, but J cross I was negative K. Okay. Then J cross J is 0. J cross K is I. So minus 4I. And then K cross I is J, minus 6J. And then K cross J is negative I. K cross J is negative I. That's minus 24I. And K cross K is 0. Okay. So let's add all of these. So minus 28I minus 8J plus 4 kilograms meters square per second. That is the angular momentum. Okay. Or rather, then they ask you, what is the torque on the particle about the origin? So this is a whole bunch of cross products. The torque is defined as R cross F. Okay? R is the vector from the origin to the point of application of the force. Okay, so when you're calculating the torque about the origin, that's the R vector. You can calculate the torque about any point. Okay. So there is R and there is the force vector. Okay. So let's calculate the torque. R is 2I minus 4J plus 6K. Okay, so torque is crossed with 10I, and the units are Newton meters. Newtons from here and meters from here. All right, so again, we'll do the same thing. I cross I is 0, I cross J is K, which is 30K. J cross I is negative K, and there's negative 40, so plus 40K. Okay. And J cross J is 0. K cross I is J, that's 60J. And then K cross J is negative I, that's negative 90I. So that's the torque. Okay. And then they ask you, what is the time rate of change of the particle's angular momentum at this instant? So we calculated all this at this instant. And what does Newton's second law say? Torque is equal to dL by dt. Okay, so the time rate of change of angular momentum is equal to torque, which is that. Okay. Okay, so this problem says a boulder of mass 20 kg and radius 20 centimeters rolls down a hill 15 meters high from rest. What is its angular momentum when it's halfway down the hill, at the bottom of the hill? So there's a boulder rolling down a hill. Okay, so I'll do it at the bottom, and if you want to do it halfway, just use a hill that's 7.5 meters high, okay? So, so again, we'll use energy conservation principle, okay? What is the angular momentum at the bottom? So the angular momentum is I times omega, okay? And omega is what we want to find. The moment of inertia for a spherical object is, so there is the moment of inertia. For a sphere about that axis is 2/5 mr squared. Moment of inertia is 2/5 mr squared. Okay. So we're going to use energy conservation principle. Initial energy is equal to final energy. Initial energy is all potential energy, mgh. And that gets converted at the bottom to rotational kinetic energy and translational kinetic energy. And that's the center of mass velocity. It's omega and v center of mass velocity. And the center of mass velocity and omega are related like that. So let's put in stuff that we know. Mgh equal to 1/2. Moment of inertia is 2/5 mr square times omega square plus 1/2 m. The center of mass velocity, we'll put it in terms of omega because omega is what we're trying to find. R omega. Okay. So mgh equal to, the 2 cancels, this is 1/5 m r square omega square plus 1/2 m r square omega square. Okay, you can see that. So if you multiply this, okay, the kinetic energy, this is translational kinetic energy and this is rotational kinetic energy. So if you divide this by that, 5/2 or 10/4, so rotational kinetic energy is 40% of the translational kinetic energy. Okay. All right, so omega is what we're trying to solve for. The mass cancels. GH is, and 1/2 plus 1/5 is 10 to 7/10 r squared omega squared. Okay. Omega is okay, so that is the angular velocity of the boulder at the bottom of the hill. Okay, so let's calculate this. G is 9.8 meters per second square. It came down a 15-meter high hill, and the radius of the boulder is 20 centimeters, 0.2 meters. What are the units?
Radians per second.
Radians per second. Okay, how do we know it was radians per second? Because we use this formula. Anytime you use linear velocity relating to angular velocity, that's in radians per second. Okay. All right, so that's the angular velocity. And what is it that we wanted to find? We wanted to find the angular momentum. Okay, so we need to multiply that by I. And angular momentum is I times omega, which is I is 2/5 mr squared.
Should it be 0.02?
What?
The radius?
No, 20 centimeters, 0.2 meters.
Oh, 20.
Okay. So you can put these guys in. The mass is 20 kgs, and then 0.2 meters square, and omega is 72.5 radians per second square. Okay, so it'll work out kg meter square per second square. Those will be the units, and this will work out to okay. So that's the magnitude of the angular acceleration for the boulder. Okay, let's do this problem first, and then we'll come to the other problems. So a merry-go-round has a radius of 2 meters and a moment of inertia of 300 kg per meter square. So here's a top view. And the merry-go-round is rotating about that axis. A boy of mass 50 kg runs tangent to the rim at a speed of 4 meters per second and jumps on. Okay, so actually, so this is at rest. And a boy is going at 4 meters per second and jumps on. What happens? What will happen to the merry-go-round? The merry-go-round was at rest. Okay, so this is a collision. In a collision, you saw for linear motion collisions was what was considered? Momentum was considered. So in this collision, angular momentum will be considered. Okay, so what will happen is once the boy jumps onto the merry-go-round will start spinning. Okay. The initial angular momentum will equal the final angular momentum. Okay. Now what we'll do is we'll calculate the angular momentum about this point, and the initial angular momentum is the angular momentum of this guy plus the angular momentum of this guy. The angular momentum of this guy is 0. The angular momentum of this guy is his momentum times the moment arm. And then the angular momentum of this guy, now that this guy is rotating, is the moment of inertia of the merry-go-round plus the moment of inertia of this guy times omega. Okay. So we have to calculate all of that. So this is a collision. Okay. And in this collision, angular momentum will be conserved. So the initial angular momentum is, for the merry-go-round, it's 0 plus mvr, the mass of the boy, okay? So 0 plus mass of the boy is 50 kgs. Velocity is 4 meters per second. And the merry-go-round has a radius of 2 meters. Kg meter square per second. That's 200, 400. Okay. The final angular momentum is the final moment of inertia times omega. The moment of inertia is the moment of inertia of the disk plus the moment of inertia of the boy. Okay. And this is 1/2 mass r squared plus mass of the boy r squared. We are treating the boy as a point particle, and he's r distance away from the axis of rotation. And for a disk, that's the moment of inertia, 1/2 mr squared. Okay. All right, so let's calculate the moments of inertia. Moment of inertia of the combined object. 1/2. Oh, well, they give you the moment of inertia of the disk, actually. They give you that. That's 300 kg meter squared. And for the boy, it's 50 meters times 2 meters squared. Plus 200. Okay, so you see the moment of inertia of the merry-go-round is greater than that of the boy. Yeah. All right, so L initial is I final omega. So the angular velocity of the merry-go-round after the boy jumps on is this. We calculated the initial angular momentum, which is that. And the final moment of inertia. So 4/5 0.8, 1/2. So the angular velocity is 0.8, and remember this is radians per second. Okay. All right, again, what this is a collision problem. So this was a merry-go-round that was at rest. This kid comes in and comes in at 4 meters per second and jumps onto the merry-go-round, and the merry-go-round starts rotating. Okay. And the angular velocity of the merry-go-round is 0.8 meters per second. Okay. Now, if you want it to keep rotating faster, what could you do?
You could have more boys jump on it.
There you go. Okay. And heavier the boys and faster they're jumping, the faster it'll rotate. Okay. So you can keep adding angular momentum. Okay. All right, I'm not going to do this problem, but I'm going to tell you what it is. Okay. So a space station consists of a giant rotating hollow cylinder of mass 1,000,000 kgs. Now, see, putting mass in space is expensive. It's only become cheap now with reusable rockets. So the space station is 1,000,000 kg, including people on the station, and it has a radius of 100 meters. So the space station would be, it's a cylinder like this, okay? And you're living here. This radius is 100 meters. So the cylinder would be from here to building 100. That would be the size of the building. Okay. Now, if the space station rotates, so you want to simulate gravity, and the way you do that is you rotate the space station like that. So if you're in there, and if you're going in a circular path, what do you need to go in a circular path? Centripetal force. So this guy is pushing you downward, and that feels like gravity. Okay, so if you rotate it at the right speed, okay, how do you feel gravity? The ground is pushing you, right? Okay. So you could have soil there, and plants would grow. The plants would grow in this direction, roots would go in that direction. Okay, so that's how they would build these space stations. Okay, the problem is, so you'll get it rotating at the right speed, so you feel 1g, because if you're going on an intergalactic journey, you'll be traveling for years, and that's what you want. Okay? Now the problem is the following. Well, you won't be going on an intergalactic journey. The best you could probably do is probably go to a close by star. Okay. If 100 people on the average of mass spacewalk to an awaiting spaceship, what is it is rotating, okay? Okay, now what will happen is 100 of these people will get on a spaceship and go away. So what will happen to the space station?
It will accelerate.
It'll rotate faster, okay? And so it'll rotate faster, and so those guys have to go radially outwards, and it'll rotate faster, and that's what, so it's a conservation of momentum problem. It's a cool problem, but I want to show you one other cool problem. This I'll solve. Now, maybe I won't solve this one either, because I want to lecture on chapter 12. Okay, this is a pulsar. Do you know what a pulsar is?
Is a rapidly rotating star that emits regular radio frequencies, or light.
Light and stuff like that. It's a neutron star. Okay, so it's a very dense star. This is at the end of, okay, so here's a star. And when a star dies, so our sun is 5 billion years old. It's got another 5 billion years to live. Okay, the mass of our sun is indicated like this, solar mass. Okay? So if the mass of a star, so this becomes a white dwarf. So when a star dies, it can become one of three things. White, okay? If the mass of the star is less than 1.4 the mass of our sun, yeah, it'll become a neutron star. If the mass of the star is between 1.4 solar masses and 3 solar masses. What will happen if the mass of the, no, it's the core that we're really talking about, but 3 solar masses?
Supernova?
It becomes a black hole. Okay? So those are the 3 states of death of a star. Okay? A neutron star is just a very heavy nucleus. So for instance, if the radius of our sun is about 500,000 miles. If our sun became a neutron star, it would become a small sphere from here to Ormond Beach. From 500,000 miles to about 10 miles. Okay, so it becomes very dense. All right. Now, so neutron star is a very dense object and it has a strong magnetic field. Now, if it so happens that this is the axis about which it's rotating, so our sun rotates about once a month, and this neutron star with this very heavy object will rotate at maybe about 800 to 1,000 times a second. Why is it rotating faster? You guys know, you've seen an ice skater. Ice skater spinning, and then you bring your arms in, you're spinning faster. So here's a star that's collapsed tremendously, and so now it's spinning faster because angular momentum is complete. Yep.
What effect does that have on the magnetic field?
What do you mean? The spin?
The spin, yeah.
Well, the magnetic field is because of the spin. It's the charged particles are producing the magnetic field.
So what, it spins really fast, what does that do to the,
Oh, the spin, because of it's spinning, if it weren't spinning, it wouldn't have a strong magnetic field.
compared to like our sun or the Earth?
Yeah, so the magnetic field is very strong.
Okay.
Yeah. So now, if the magnetic axis does not coincide with the spin axis, okay, then along the magnetic axis, you get a strong beam of radiation. Okay, so now let's say, so here's the star spinning, there's the axis of the spin, and here let's say this is the magnetic axis. Okay, so along, it's like a what do you call those, lighthouse. Now the beam, if it's spinning like this, you're getting a beam that's spinning. If the magnetic axis coincides, then there's no beam spinning. So and if you happen to be there, then you can see it, but you would see a continuous beam. But if it's spinning, if the axis doesn't coincide and it's spinning, now if you're there, you're seeing a beam once every millisecond. It's spinning 1,000 times a second. That's why it's called a pulsar. And the lady who discovered it, she was an Australian lady, discovered it in the 60s. She's come here several times and given a talk. I mean, to this town, yeah, at Embry-Riddle. And there are people who know her, so she might come again. Jocelyn Bell. Okay. There's a poster in our hallways about her. Okay. So that's a neutron star. All right, that's what the problem is about. I'm not going to solve it because we are out of time. You guys take a 5-minute break, and then we'll do a lecture on chapter 12.